Hello there, my calculus students. Dr. John Troggy here, and we are working now on section 4.2 in your book. The chapter is called Linear Approximations and Differentials. And rather than working at my whiteboard, I'm working down here, instead capturing my screen because I can't resist using Desmos for this topic. This topic is near and dear to my heart. This is actually hugely important stuff that we used to do back when I was in my old job doing atmospheric science stuff. This technique was actually something that happens a ton in sciences. And so I'm actually pretty excited about it. On the other hand, well, in the context of a calc course, we learn about it in this lecture and then kind of never come back to it. In fact, if you wanted to learn more about this, there are whole math courses about this. I took one back at Purdue. It was a 400 level class, something like mathematical methods or something like that, or arithmetic methods, something like that. It's actually a very important technique that explains how calculators come up with values like sine and cosine, and for that matter, how you could come up with values of things like sine and cosine without a calculator. It's actually hugely important, but we only spend a little bit of time on it in this class. But here's what we're going to be doing here. If you have some function, by the way, please get yourself a copy of this linear approximations and differentials handout. Whether you print it or not, it's kind of your business. But get it so we can be following along here. And so what I want to talk about is if you have some function f of x, well, actually, we've had plenty of problems already where we ask you to find the equation of a tangent line for some particular value point along that line. We'll call that point along the line A for now. And let's actually work through an example here. Now, in the example here, I'm saying find the line tangent to this simple function, f of x is x squared, at the point where x is equal to 0.5. Let's bring up Desmos and make sure we understand what's going on here. The function that we're plotting is f of x equals x squared. And we want to make a tangent line to that at the place where x is equal to 0.5, down here. All right, well, actually, that is not a hugely difficult thing. We've actually had problems along that wet line where we did things like compute the slope of the tangent line, m tangent line, which was just equal to the derivative of that function, in this case 2x, and then you plug the value of x that they're giving you, in this case x is equal to 0.5. So you plug that in, and 2 times 0.5 is equal to 1. All right, that would be the slope of the tangent line there, and then we now have a slope, and we have the point. It's at the x is equal to 0.5 and the y is equal to whatever f of x is. 0.5 times 0.5 is 0.25. So we could actually just plug in, that would be our x naught is our original point, and we could use the so-called point slope form of the equation here. But for today, because of the thing we're going to be doing, I'm going to actually rearrange the point slope form of the equation. It's not quite so clear how this comes to point slope form, although all it is I'm moving, this was y minus f of a equals, and then the rest of this, I just moved it to the other side. But this is an important rule to know for today's assignment. The equation of a tangent line is going to be y equals f of a, the place that we're working with, the point that we know, times the derivative of f prime at a, times x minus that same a. So in this case here, this is, by the way, this is like hugely important. I don't know if I can like highlight this or something for you. That's a hugely important equation to know. So like in this problem right here, we're going to just work through this here and see that the slope of our tangent line, our equation of our tangent line will be f of a plus f prime of a times x minus a. Okay, f of a is f of 0.5, which will be a quarter, because remember f is squared. So 0.5 squared is 0.25, plus f prime of a, which is f prime of 0.5. Well, f prime of 0.5, remember f prime is 2x, so f prime is 1, because 2 times 0.5, times the quantity x minus a, where a is 0.5. And with a little rearranging, that turns out to be y equals x minus 0.25. And you could write that however you want to, point slope form, or slope intercept form is actually what I have right there, or whatever you want to. And let's actually go over here and write that a function here. Y equals x minus 0.25. And you can see that, let's zoom in a little bit, that it is tangent to the curve. See how it's tangent to that curve at the point that we asked for, where x is equal to 0.5. And it looks good. It looks darn good. Oops, I'm on the wrong document there. And so when we look at these in Desmos here, what I want you to notice is what happens if we start zooming in. So here's our original function, f of x. It's this parabola here. And we've made this linear function, this blue thing here, which is y equals x minus 0.25. Pretty straightforward here. What happens if I start zooming in? And I zoom in more, and I zoom in more, and I zoom in more. As I get closer and closer and closer to our original point here, where is that here? 0.5 right here. Notice that it gets harder and harder to tell our parabola and our straight line apart. In fact, the value, like at any given x here, the value of f of x, which is the green line, and the value of that linear function we had, which is the blue line here, are practically the same. Fairly close to that point we started with. The two curves are basically this, well, one's curve and one's a line, are basically the same thing. In fact, we could say now that this simple linear function is a good approximation to this function. And that is a hugely powerful tool. Let's go back over here for a minute to look at the handout some more. As we zoomed in closer, once we have made that tangent line, what we see is if we zoom in, the area around where that tangent line is touching our original curve, the tangent, I even highlighted that yellow, the tangent line approximates the original function. It's close to it, which means we could use the tangent line's function, which is very simple. It's always just a slope and an intercept kind of thing, to approximate the original function, which might be really complicated. It might be things like sines or cube roots or something like that. And we can approximate and get approximate answers here. This is a hugely powerful technique. We're going to be taking complicated curves like parabolas and hyperbolas and God knows sine waves and God knows what else. And we're going to be able to approximate them with these very simple linear functions. And probably the best one we could do as an example. And let's just go ahead and do example 4.5 in the book. Hold on, I need a drink. All right, this is example 4.5 in your book. Feel free to follow along in the book or on this handout or whatever. But the instructions on the problem say, find a linear approximation to this following function at x equals 9 and use that linear approximation to find the square root of 9.1. Okay, I realize that these are not the most clear of instructions. Here's our original function. F of x equals the square root of x. Oh heavens, let's go plot that. F of x is equal to the square root of x. And go back home here. There it is. Okay, the truth of the matter is square root is a complicated thing to compute. If you needed to compute the square root of 9.1, which is what the problem is asking for, and you didn't have a calculator or the calculator didn't have a square root button or something, this would actually be an incredibly complicated thing to do. It is not a simple thing to come up with the exact answer of the square root of weird numbers like 9.1. But we are learning that we have a technique that can make a linear approximation, a simple line that will be very, very close to the right answer. Again, I went the wrong window here. All right, so let's actually figure out how we're going to do this here. In our problem, we're given that A is 9. That's the point we're going to be working with. Well, f of A then is f of 9, which is equal to 3. And for that matter, we can compute the derivative of f of x, f prime of x, and it's 1 over 2 times the square root of x like this, kind of an awkward thing. But then we can figure out what is f prime of A. Well, A is 9, f prime of 9, which will be 1 over 2 times the square root of 9. Square root of 9 is 3. So this will be 1/6. And now we have all of the terms that we need to compute some kind of linear function, which we'll call L of x. All right. We were using y earlier, but L of x will be fine. We're going to use that terminology in here. So L of x is equal to that same idea, f of a plus f prime of a times x minus a. All right. Well, we have the f of a. It was 3 because a was 9. F of a is the square root of 9, which is 3. Plus it was f prime of a. F prime of a we did before, it's 1/6. times the quantity x minus a, and a is 9. All right, with a little bit of rearranging here, we could simplify this function. We don't really need to, though. I mean, it's fine just like that. Let's go over here and plot that thing. We'll call that L of x is equal to, it will be happy with L? It might not be. Yeah, it's okay. It was what? 3 times 1 over 6 times the quantity x minus 9. All right. At the place x equals 9, which is out here someplace, at x equals 9, look how close those two curves are to each other. It's pretty much impossible to tell the difference between the red curve, which is our straight line, and the black curve, which is our very complicated x square root of x. But I know if I needed to sit down at a calculator, I didn't have a square root button, this thing would be really hard to compute. This thing, I wouldn't even need a calculator to compute. I could compute these things no problem because I passed, third grade arithmetic. I could plug in values of x and get this thing. Now, what the problem is actually asking here, let's go back to the handout here, is use that to find what is the square root of 9.1. Well, we know f of 9.1 is going to be really, really close to L of 9.1. Remember, f and L, let's go back to the Desmos window. F is our black curve, L is our red one. And in the neighborhood of 9, these two things are pretty much the same. Yeah, if I was over here someplace, they're very, very different. But in the neighborhood of 9, like 9.1, these two things are basically on top of each other. So if I go over here to my linear functions here, I'm going to go ahead and compute L of 9.1. That's going to be 3 plus 1/6 times 9.1 minus 9. And you crank that through on a calculator, or you do it in your, with on a piece of paper, whatever, and you get 3.016667. That is not the value of the square root of 9.1, but it is darn close to the actual value of the square root of 9.1, which actually is 3.01662, and goes on. But we got like the first 5 or 6 decimal places right, which for many purposes will be good enough. See how we took something really complicated. If I had told you to go compute the square root of 9.1 and you can't use a calculator, oh my goodness, how would you even start? But this, I mean, I don't know that I would love doing 3 plus 1/6 of this difference here, but I bet I could do it. I mean, you certainly could do it back in grade school. It was just a matter of, multiplying fractions and all that kind of good stuff. It would be unpleasant, but you could do it. Well, this is great news. And in practice, by the way, it's hard to overstate how important and amazing this is. In practice, that is what your calculator is really doing. If you've ever wondered, how does your calculator know what the square root of 9.1 is? In fact, it's using techniques like this. Now, it's using a slightly fancier version of this technique where it's not necessarily a line, but it has that kind of idea where it takes a place it knows the answer, like we knew what the answer of square root of 9 was, and used it as a way to find the answer at a place that was close, like 9.1. Square root of 9, easy problem. Square root of 9.1, impossibly difficult until you use one of these kind of techniques. This is going on behind the scenes every billions of times a second when you're playing a video game, when you are doing anything that involves calculations on your computer. Behind the scenes, this is how sines and square roots and logs and stuff like that are actually being computed by the chip. It doesn't have some giant table in there that says square root of 9.1 is this, square root of 9.2 is this. No. It uses techniques like this to find that for you. Let's do another example like this. I need another drink here. This will be example 4.6 from your book. And it says it wants you to find the linear approximation of f of x equals sine of x at the value pi over 3, and use that linear approximation to come up with the answer, the approximate form of the sine of 62 degrees. In case you didn't know, pi over 3 is 60 degrees. So this is a place, we're going to take a place we know because we can look it up in a unit circle. I got a unit circle sitting here on the chair next to me. And we can take a place we know and then use this linear approximation to find this place we don't know. What the heck is the sine of 62 degrees? So in this problem here, A, the point that we know is pi over 3. And we're going to need f of A. Well, f of A is f of pi over 3. F is sine, so this means sine of pi over 3. And feel free to go look it up on your unit circle over there, but it's square root of 3 over 2. All right, we're also going to need f prime of a. F prime of a, well, f prime of x, if f of x is sine, f prime of x is cosine. So f prime of a is cosine of a is pi over 3. Cosine of pi over 3, that might be one you know, that might be one you look on your unit circle to find, but it's 1/2. Okay, so then our linear approximation, big L of x, is just f of a plus f prime of a times the quantity x minus a. Well, f of a was square root of 3 over 2. F prime of a was 1/2. X minus a is x minus pi over 3. And that makes a lovely graph. Heavens, what am I doing? We have graphs right here. Let's go make them. Our original function was f of x equals sine of x. And we have made a linear approximation to that. We'll call it L of x is equal to, and of course, I've already forgotten it. Let me go back over here. I'm going to jot this thing down real quick here. It's square root of 3 over 2 plus 1/2 x minus pi over 3. Okay. Let me go put that into Desmos. This is going to be the square root of 3 over 2 plus 1/2 times the quantity x minus pi over 3. If we take a look near our point pi over 3, which is right here, I mean, in general, this curve doesn't look that much, it doesn't really look anything like the blue curve. This green curve doesn't look anything like the blue curve. But as I zoom in and zoom in and zoom in, as we get closer and closer to that real place right there, these two things are actually practically right on top of each other. In fact, I can keep zooming in as much as I want to. And at some point, it becomes pretty hard to tell the difference between the blue curve and the green curve. They are basically the same thing in that neighborhood. And given a choice of sitting down and computing sine of x or computing this simple linear function here, I'm going to choose the simple linear function anytime. And in fact, that's what the problem is asking us to do. It's asking us to plug in 62 degrees for x so that we are finding this linear approximation to the sine of x. Now, there's a little bit of a sneakiness here that you have to actually change that 62 degrees to radians. Let me know if you don't remember how to compute degrees and radians back and forth from each other. But then we just plug that value into our linear approximation. Here's our linear approximation. L of x is square root of 3 over 2 plus 1/2 times the quantity 3x minus square root, I'm sorry, that's not square root, pi over 3. And plug in that value, this weird long number, 1.8 something, is 62 degrees in radians. Plug it in, chug, 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 plug it out, and you get this number. This is our approximation to the value of a sine of 62 degrees. 0.88347, and it keeps going. Turns out that's not half bad. I went over to a calculator and actually plugged in sine of 62 degrees, and I got 0.8829. Okay, well, it's not, it's close to like 1 part in 1,000. I mean, that's actually pretty darn close right there. So this was a slick trick. I really like these. And we'll do, should we do one more example here? Let's do another example. Let me go over to your chapter for today, and let's look at problem 52. All right, this is one that you are not doing here, but the problem is f of x equals the tangent of x, and it says make the linear approximation to that at a equals pi over 4. Where should I do that? Let's go back over here to your linear document here, and I'm going to actually do that right here in front of you. I'll call that bonus problem 52 from the book. This is not one of the problems that you're solving, but it'll be fine. And so f of x is the tangent of x, and we say find the linear approximation at a equals, I'll just write it pi over 4. Okay. All right, so how do we want to do this here? We're going to say, let's go over here. I'm going to bring up some math. Let's say that we want L of x is equal to f of a plus f prime of a times x minus a. And f of a will be Our function is tangent, and a is pi over 4. The tangent of pi over 4 is 1. Again, feel free to look on a unit circle or something like that. The tangent, the f prime of a. F prime of a is the derivative of the tangent. Derivative of tangent is secant squared. Secant squared is the same thing as 1 over cosine squared. All right, so I messed around with this here. Secant of pi over 4 is square root of 2, but it's secant squared, so the answer is 2. All right, I don't want to mess with all that right at this moment here. But derivative of tangent is secant squared, which the secant of pi over 4 is square root of 2. And then if it wasn't secant, it was secant squared, so it's 2. And then x minus pi over 4. And this is a simple linear function. I mean, with a little rearranging, we could put this into point slope form, or we could put this into slope intercept form, or whatever. And that's all that that problem is asking for here. Insert that in here right here. And let's actually compute that one. Let's go and actually do it in Desmos. All right. F of x equals the tangent of x. Oh, what an old friend. What an ugly looking little thing right here. But we're saying that we think our linear approximation to that is, let's use L of x, is 1 plus 2 times the quantity x minus pi over 4. And what we see here is that this function is very much, I mean, yeah, the two curves are quite different down here, but if I get closer and closer to that original point that I had, let's zoom it in, zoom it in, zoom it in, after a while it gets hard to tell the blue curve and the black curve apart. Computing tangent of x is a pain in the butt. But for some area around here, for some range, for some domain of x's that are near the original x equals a place, this would actually be a really good approximation and would be a whole lot easier than trying to compute tangent. Cool. Oh, I love that stuff. Now, the rest of what happens in today's assignment, I mean, well, is kind of, well, it's kind of making sure we're clear about some terms here. And this is this word differentials. Everybody gets turned around because of, like, man, there's so many words in this class that start with def or diff. Differentials are not as big of a deal as the book is making it sound like it is. What we need to do is just remember that in that Leibniz notation, dy dx is another way of saying that is another way of saying f prime of x. Now we could multiply that dx part over to the other side and say dy equals f prime of x times dx. All right, I know you're thinking, wait a minute, I thought that dy dx, that was just a way of writing the derivative, but now we're actually taking it apart. Leibniz liked things like this. He called those parts differentials. And what do they mean? Well, remember back when we computed like the slope of a line, we had like the change in y and the change in x, and we generally wrote them as like delta y and delta x. Well, delta is the Greek letter for what we call d. See how they're kind of a match like that here? So basically what we're saying here is if we have some little change in x, what's the corresponding change in y? Like what is the slope of this here? A simple problem, you're going to look at this and say, well, I can't believe they even took time for us to do this. Like, for example, here's example 4.8 in the book. Here's a little function, f of x is x squared plus 2x. And it says find dy and evaluate it when x is equal to 3 and dx is 0.1. This differential is 0.1. So like if I change the x, if I go out to x equals 3, and then I move out a delta x of 0.1, what will be the corresponding delta y? And well, okay, once you know that there's this relationship dy equals f prime of x dx, all right, well, dy is easy in this case. It's just 2x, f prime of x is easy. It's 2x plus 2 times dx. Okay, remember, we move that dx over to the other side. And the problem tells you the value of x, and the problem tells you the value of that differential dx. So you plug them in here, and you get 8 times 0.1 or 0.8. So your answer is the differential dy is 0.8. So like if we were talking about the slope of that tangent line, if you went out, what was dx? Dx was 0.1. So if you went 0.1 out on it, you'd go 0.8 up. not as big of a deal as it seems. Well, that's not true. Actually, later on, like in science and stuff like that, this becomes a thing that we use to like approximate changes and stuff like that. But it's not the biggest deal. You don't have that many problems about this. All right, so let me go show you the assignment here. It is a little confusing how this works here. First off, I want to point out that this assignment is not due until Wednesday, April 8th at the end of the day. Remember, EBSC is giving us like 2 weeks to do these assignments in case you have family emergencies or internet problems or whatever. But I don't recommend really waiting that long. I think that would serve you. The assignments that I'm giving you are problems 51 through 67 odd, plus problem 73. Now, a group of those problems, I think it's 6 of them, the problem actually doesn't give you the value of A, that point that we know at the beginning, and it kind of wants you to try to compute it yourself, but that seems like an unnecessary step. Well, what am I meaning by that? I mean, it seems like that would be the kind of place where mistakes could get made. So rather than having you compute that part, I'm going to give you, for those 6 problems here is the value of A that will work well for you. Go ahead and have that piece of information when you do that problem set. All right, so you have a handful of problems here. What is this? Maybe 8, 9 problems, maybe 9, maybe 10. I'm not sure. 9, I think. And there isn't a small exit ticket afterward. I think it only has one problem about these linear approximations. And then after that, I think it's all review questions. Anyway, just kind of making sure that everybody's staying on the same page and so on. All right. Well, I think that's everything that we needed for today. I kind of missed my dry erase board, my tiny little dry erase board. On the other hand, the other day when I recorded the lecture, I really missed Desmos. So, all right. Hopefully you're all taking care of yourselves and your loved ones. I hope everyone's okay in this time. And please let me know if you or your family have any questions.